Today I'll present you my journey towards learning how to scale WebSockets. And I'm not a specialist in this topic. I just conducted several experiments, and I will show you. I was already introduced, but the main point about me that I'm a Python enthusiast, and I mostly specialize in backend development using Django framework. My presentation consists of 4 parts. First, I'll tell what WebSockets are and why are they special and what's the problem. Then I'll show you how we can load test WebSockets, and I'll present results from load testing Django channels and AWS WebSockets. So these are 2 main technologies which can be used for WebSockets using Python. So almost whole internet uses HTTP, which is just a client sends a request and server response. So this is one directional communication, and WebSockets allows to add bidirectional communication, but this extension adds additional limitations or additional requirements for your infrastructure. So I wanted to learn or to get to know what those limitations are, and whether should we add WebSockets to existing projects or not. Usually backends are simply serverless REST APIs, which can easily scale horizontally. You simply add additional machines, and they take the load. So a client can send several sequential requests, and these requests can be handled by different machines, and this allows to balance the load easily. Let's say we have one of these products, which are serverless REST APIs, and we want to add WebSockets. And what should we consider? WebSockets open a connection, and this connection have to be open whole time. So all active users become your headache. You have to consider not only how many simultaneous or concurrent processes you should be able to handle, but also how many active users are there. Second concern is can a user which is connected to one machine broadcast messages to other clients which are connected to different machines? And third concern is what happens if we try to add additional machines, and if we try to scale horizontally. and how does the number of requests per second changes when we add additional machines. So I have conducted several experiments, and let's see what I have found out. In order to check how the load is handled, I had to choose a load testing tool, and I chose Locust. And this Locust framework is well supported, mainstream, time proven. It can handle millions of concurrent users if you use a distributed system. And it's written in Python, and it has a very nice graphical user interface to display the charts. And it works by increasing the active user count. Every second adds several users, and these users are added till servers start to respond with errors, or the response times increase significantly. So I have investigated this Locust framework, and I found out that it only supports HTTP methods. So that's that. And so by default, I couldn't use Locust to test WebSockets, and I have investigated the code base of Locust, and it seems that the code base is pretty simple. It simply wraps API calls made with requests library. So just uses this method, which collects some metadata, then executes API call using request library, and then logs the event, creates a data point in the chart. Having this, I thought that it would be possible to collect metadata by myself and use the same method to log events to make these data points appear in the chart. Yeah. This is a simplified version of Locust code, but basically it is what it does. I have created a Locust user which uses Websocket Client, and first I have created two helper methods which allows to log success data point or failing data point, and I have added the default values for unmeaningful attributes. Then I created a Websocket client. This client is asynchronous, and it accepts two handlers. One is for one is executed when connection is opened, and another is executed when Websocket client receives error from the server side. In order to execute this asynchronous WebSocket client, I decided to run it in a separate thread. So I have created a listener thread which receives all events from the server, and this main thread is executed for tasks, and basically it sends messages to the server, or in this case it does nothing. Okay, so let's see whole worker or user class. So this class is for testing how many open connections can the server handle. So this worker starts a Websocket Client and waits till connection is received. And when the connection is received, we log a success data point, and if we time out or receive an error, we log a failing data point. And one more thing to mention is that this onStart method is basically for worker initialization, and we have to wait till the connection is received from the server before starting our tasks. Otherwise, we would get an error because the connection is not open. So for that, I have used a semaphore, which is thread safe, and I block this onStart method till connection semaphore value changes, and this semaphore is changed on open event. So I have created another WebSocket user, which is for request response throughput testing. So basically, I wanted to investigate how many open connections can a server handle, and what is the request per second throughput for open connections. So the two measures which are important. And the second user class does the same. It initializes the Websocket Client, and we have to add more handler methods. So for incoming messages, and for incoming messages, I have used queue, which is also thread safe class, and it allows to exchange data safely between multiple threads. And when a message is received, I simply put that message on the queue, and that's all. Also, if the connection times out, this time I don't log failing data point. I simply stop the user, and let's see how the task looks like. Basically, I send a message and wait for response. And when the response is received, I simply log the successful data point. And that's it. And let's see what we can get with these user classes. I have tested two architectures. first one is implemented using Django channels. So you can see a schema here. And this is a containerized implementation. So we can add additional containers for each component. And my main concern was what happens when we add additional Django containers. And this implementation is for Django channels, and channels have Redis and Daphne dependencies, and usually when writing consumer code, you don't have to modify the Redis or Daphne in any way. So these two components are basically black boxes. You just write a consumer and everything works, and it's hard to guess how Django channels behave when multiple containers are added. So I have created two containers and tried to broadcast a message. You can see that one container uses 18 port, and another client uses 888, and they are separate. They don't impact each other in any way, but two contact points exist. They both connect to Redis and to PostgreSQL database. PostgreSQL database is not used in Django channels, so basically the single contact point is Redis. One outcome could be that the first client is isolated from the client 2, but I have tried, and success, the message was broadcasted correctly. So that means that we can add multiple Django containers, and they all would be added to the same channel, and they would receive all broadcasting events. So that's really great news. And I have executed the experiments. First, I tried to understand how many open connections can this single container handle. I have run this containerized implementation on my personal server, which is not very resource rich. So I think that all my measurements could be scaled by a constant if a more capable server was used. So the result from this experiment was that a single container could handle almost 2,000 open connections, and after that no more new connections would be accepted. So probably I should explain the charts. So the green line shows how many requests were made, and these requests are new connections being made. All previous connections are not counted to newly added points. So we can see that every second the 50 new connections are being made, and the response from these the request to open new connection gets rejected. So the green line is a sum of two values. It's successful connections and failed connections. So when green and red lines match, that means that all of the connections were rejected. So yeah, and the second graph shows that the response times at the beginning they were to 200 milliseconds, and when a lot of errors became popping up, the response time decreased significantly, meaning that probably Nginx reject the connections. So the bottleneck was Nginx container. And I have conducted the same experiment using two containers, and the result was the same. And total open connection number was equal to almost 2,000. And that confirms that Nginx could be the bottleneck in this case. Okay, let's see another experiment. So this experiment tests the response throughput. Client sends a message and waits for a response. And with a single container, we can observe that 20 requests per second were handled. And well, it's what it is. My server is not very capable, but we can see that when the number of users increase, the successful response, the number of successful responses decreases, and until the point where almost all requests are rejected. I have executed the same experiment using two containers, and throughput increased, and it doubled. So now we can see that the successfully handled requests per second are equal to 40. So that's exactly the double. So that means that when we add additional containers, the throughput increases linearly. Well, I have tested only with two containers, but in this case, that's true. And so what conclusion can we draw here? That horizontal scalability actually works with Django channels, and you can add additional containers, and they all get broadcasted messages, and they increase the requests per second capacity linearly. Now let's move to another architecture, which is AWS based. this architecture is way simpler. We have an API gateway, which is connected to Lambdas, which can have concurrent executions. And we also use a S3 bucket to store connection IDs. It's really important to know that AWS has a lot of restrictions, and I have pointed the main ones here. The API gateway, the main restriction of API gateway is new connections per second, and this is the main limiting factor. There is no such limit for total number of connections, but the total number of connections is limited by number of new connections appearing. And using this number, 500 per second, you can get almost 4 million users connected by default. Message size is quite small. For Django channels, it can be tens of megabytes, and here we have only 32 kilobytes. And all WebSocket connections are terminated after 2 hours. There are additional limitations for Lambda functions, and these are that you can have only 1,000 concurrent Lambdas at a given point. Each Lambda can run only 15 minutes, and when you need additional Lambdas, they are spawned not instantly, but the limitation is 500 new Lambdas per minute, and almost all, not all, but the most important quotas can be increased. You simply have to justify your need, and you can increase the number of concurrent Lambda executions to up to 100,000, and I guess the same applies for new connections per second. So I have executed the same experiments with default quotas, and I had 500 new users per second for API gateway, and we can see that that's actually true. I tried to create 600 new connections every second, and those 500 were connected, and the remaining ones were throttled with too many requests error code. So I was able to connect 30,000 users in 1 minute, and the lines started to drop because my computer started. Well, the load was too high of my computer. Memory was exhausted. So I have conducted another experiment for a request per second measure, and I have observed that the actual throughput was almost 7,000 requests per second. So that means that compared with 40, it's really big number. One point that these requests per second were throttled because I have reached 1,000 concurrent Lambda executions. But this number can be easily increased, and we probably could have 100 times bigger request per second number. If we increased the concurrent Lambda limit to 100,000. And I had this feeling when I was conducting these experiments whole day, and I was looking at my bill, and I saw that, oh, that's few cents, that's great, I'll conduct more experiments. And the next day I saw that the bill is calculated only every 1 day. So have that in mind. But the bill was not so big. It was only a couple of bucks. So I got very high throughput for quite a low cost. So the conclusions are that it is possible to use Locust for load testing, and Django channels can be horizontally scaled, but Redis is the only limiting factor. You can scale it vertically, and you can have Redis cluster and similar techniques. And it is really the last conclusion is that AWS allows us to ditch very hard problems by using AWS Lambdas. And CCT is firing. Just have that in mind. And thank you. Do you have any questions?